Unlike direct current, alternating current reverses direction of flow periodically. Rectifier is a device which converts alternating current to direct current. It does this by cutting off one of the half cycles of an alternating current so that it becomes a pulsating direct current flowing only in one direction. In the earlier era, vacuum tube diodes were used as rectifiers. Now there are semiconductor diodes which are commonly used in hobby electronics. Other types of rectifier devices are mercury arc valves, stacks of copper and selenium oxide plates, and silicon controlled rectifiers. Rectified output needs smoothing out of ripples using high value capacitors and inductors. Voltage regulation is done by devices like Zener diodes to provide a stable output in the face of potentially fluctuating loads, as in amateur radio transceivers. Transceivers need high current during transmit mode and only very low current during reception of radio signals. These are a couple of rectifier diodes which can be used to convert AC to DC. This region is the cathode and this region is the anode. The cathode is marked by a ring. You can see a small ring, white ring here. Here also the ring is there, though it is a little more faded. So this will be anode and this will be cathode for the diode. Diode by definition allows current to transfer only in one direction, and by notation, current in an electric circuit is from anode to cathode, though actually the flow of electrons is from cathode to anodes. Conventionally it has been designated that the current flow is from anode to cathode. So these are a couple of rectifier diodes. Now we will see how they are used in rectifier circuits. We saw that cathode is marked by a ring on the actual device, and this is the electronic symbol of the anode and cathode. This is the anode and this is the cathode. The corresponding semiconductors are like this. It's a PN junction which allows transfer of electrons only in one direction. This is positive type, P type, and this is N type semiconductor. So this is a PN junction in this diode, and this is used for rectification. This is a transformer which is shown here, primary winding and secondary winding with the core in between. Here giving an alternating current here. Sinusoidal alternating current waveform is fed into this primary, and secondary also will have an alternating current. Only difference, depending on the turns ratio, the voltage will be different. This is like a step down transformer I have shown. You can have also step up transformer. And this circuit uses only a single diode. So the lower half of the alternating current will be cut off by this diode when it goes into the load. Load is a resistor. So you will have only the upper half of the current flowing through the diode. That is rectification. So as one of the waves are cut off, it is a half wave rectifier. Only the positive cycles are sent out into the load. That is a ripple like, intermittent ripple like current which flows into the load resistor. That is half wave rectifier. Output has only half of the waves in the input. One disadvantage of half wave rectifier is that it delivers only half the cycle of alternating current and hence the output is low. Pulsating direct current output of the half-wave rectifier needs more filtering or smoothing network to produce a steady direct current output, as the waves are intermittent and at the frequency of the alternating current. Conversion ratio eta, sometimes called efficiency, of half-wave rectifier is about 40.5%. But a center tap transformer is not necessary for a half-wave rectifier. If you connect the output of a half-wave rectifier into a loudspeaker, you will have a ripple sound with 50 Hz frequency. That is what is the output current of a half-wave rectifier. If you connect it to an oscilloscope, you can see the pattern there as I have shown in the drawing. Now this is a full wave rectifier. This is a transformer again. A difference in this transformer is that secondary has two sets of windings, or rather it has a central tap. CT is central tap. There will be windings in this side and winding this side, so that the current fed to each diode will be 180 degrees out of phase. Direction is different. And center tap goes to the part of the load, and the output from the two diodes are combined together and given as the other pole. This is full wave rectifier, because during one half of the cycle current will flow through one diode, and during the second half of the alternating current cycle current will flow through the other diode. That is why it is called as full wave rectifier. The output form will be better. This will have the double frequency sound if you connect to a speaker. That is, if you are connecting 50 Hz supply, then it will be a 100 Hz. That was one type of full wave rectifier using diodes. Now there is another known as, this is the bridge rectifier. Bridge rectifier, where a bridge of 4 diodes are used. The advantage here is that you don't need a center tap for the transformer. A simple transformer is used without central tap, and the diodes are connected in such a way that it behaves like a full wave rectifier. So this is another way of implementing full wave rectifier. The output will be same pattern which I have shown earlier. Now, as the output of rectifiers have ripples, that has to be smoothened out. That can be done by putting a capacitor across the output. A high value capacitor, typically 1000 or 2000 microfarad capacitor, can be connected across the output. Then the ripples will be smoothened out. If you want to still smoothen out, an inductor can be connected in series here, then it will be still smoothened out. Most basic rectifier circuits use only capacitors, and if you want a perfect near direct current like output, then you can use inductor in series as well. The full wave rectifier utilizes both halves of the input alternating current cycle using two diodes, unlike half-wave rectifier, which utilizes only one half cycle with a single diode. Hence, full wave rectifier yields higher voltage output. Conversion ratio of a full wave rectifier is about 81%, but a center tap transformer is needed for this type of full wave rectifier using two diodes. Conversion losses occur in the transformer and the rectifier itself. A full wave bridge rectifier using 4 diodes does not require a center tapped transformer, but there is voltage drop across 2 diodes instead of 1 in usual full wave rectifier during each half cycle. Voltage drop across each silicon diode is about 0.7 volts and can be significant in low voltage rectifier applications as the diode does not conduct when the voltage in the cycle is below 0.7 volts. I need 4 rectifier diodes for building a bridge rectifier power supply. I have them here. You can see 4 of them. If you look at this zoomed image, you can see that there is a ring here. There is a ring here on the one end of the rectifier diode. Here also there is a ring in this region also, but it is not so clear in this zoomed image. The ring will correspond to this portion, that is the cathode, and the other part will correspond to the anode. That is how you connect the rectifier diode in the circuit. Now I have roughly made the bridge configuration. This diode will correspond to this one. This diode will correspond to this one, and this diode will correspond to this one, and the fourth one will correspond to this. You can see that these 2 points are on the same line, so that it will be connected with the metal strip on the reverse. Similarly, these 2 will also be connected with the metal strip, and these 2 will be connected, as well as these 2. So there are 4 connection points in the bridge which we will have to connect to other elements in the circuit. Now I need a high value filter capacitor to smoothen out the ripples in the rectified DC. So here I have a 1000 microfarad capacitor. The working voltage is 50 volt, which is well above the 12 volt power supply which I am planning to make. And this being an electrolytic capacitor, you have to think about the polarity. This is the negative part with a smaller pin and longer pin for a positive one. Now I have placed the capacitor in such a way that the positive pole is here. This will correspond to this region because it's in the same line, in the same row. You can see that it will be here. It is the same as this connection over there in the circuit. Then you have the negative pole connected here, which is same as here, and will correspond to this region. So I have completed the bridge. Now what remains is I have to connect the transformer from these 2 points. Here one lead of transformer should come and another lead should come here in this place, that is corresponding to this and this points. That has to be connected. Then you need wires to connect to the load. I am not showing the load here. Now I have connected 2 jumper wires, one corresponding to the negative terminal here. This is the negative terminal, and another corresponding to the positive terminal. I have given color coding also, black for negative, which comes from the negative of the capacitor, and the positive one which will be corresponding to the positive pole of the capacitor as well. So this is the output of the power supply which I connect to a load, whatever circuit you are going to drive with this. The final part I will have to connect the transformer. This is a transformer which I can use for the power supply. This is a secondary output. You can see 2 wires going, that will be 12 volts, and this is the primary connection to the mains supply. The turns ratio will decide the voltage in the output. Suppose this is 230 volt and this is 12 volt output. That's a step down transformer, and you need a turns ratio of 230 to 12 to get a step down transformer. The number of turns will be much higher than 230 because you have to cover the current needed, and sufficient impedance to the alternating current should be there. So the number of turns will be much higher, and on the higher voltage side, as the current is lower and the voltage is higher, you will use thinner insulated copper wire, and on the secondary side, as the current will be more and voltage will be lower, you use a thicker insulated copper wire. That is the usual pattern in step down transformers. I have just removed part of the cover of the transformer just to show the laminated core. You can see that this core is made of several laminated sheets, and the lamination is needed to prevent eddy currents. The core will have eddy currents, will heat up the core, and that can be prevented by using a laminated core. And when eddy currents are there, that will cause generation of heat and loss of energy, so that the efficiency of the transformer in converting the power will be reduced if you use core without lamination. Core with lamination will improve the efficiency of the transformer. This is the bridge rectifier which I made a few days back, and it has been connected to a step down transformer, and I am now checking the output voltage. You can see that the output voltage is shown as 13.18 volts DC. This is the DC voltage I am getting from the bridge rectifier. You can see that the bridge rectifier has a filter capacitor and 4 diodes. The output voltage of a rectifier circuit can vary due to multiple reasons. As the load varies, voltage drop in the internal resistance of the power supply also varies, increasing with an increase in load current. Variations in alternating current mains supply cause variations in the direct current output voltage. Output of semiconductor devices can vary with temperature. Hence, some feedback arrangement acting as a voltage regulator is employed to overcome these variations in a regulated power supply. Output voltage of a regulated power supply remains stable in spite of the possible variations mentioned above. A simple way to regulate the voltage is to connect a series resistor to drop source voltage to the required level and a Zener diode to shunt with reverse voltage equal to the set voltage. The Zener diode dumps current to maintain the set voltage if the input voltage rises above that. As Zener diodes have both voltage and current limitations, this simple regulator is usually employed only in low voltage, low current circuits. This method is also inefficient as it dumps excess current which is not available to the load. Zener diode is a special type of diode designed to allow current to flow backwards when a certain set reverse voltage known as the Zener voltage is reached. Cathode of the Zener diode is connected to the positive side of the supply. Zener diodes are there with wide range of voltage and power ratings to be chosen as per need. Another option is to use a 3-terminal integrated circuit as an active regulator. It contains a precision reference, a high gain error amplifier, temperature compensated voltage sensing resistors and transistors, and a pass element. Some devices have thermal shutdown, over voltage protection, and current fallback. Current fallback is a current limiting feature so that when the load attempts to draw more current from the supply, fallback reduces both the output voltage and current well below the normal operating limits. When there is a short circuit, current is typically limited to a small fraction of the maximum current by the fallback mechanism. That reduces the risk of fire and damage due to heat.